Okay, so this is a paper. Kelvin and I have been working on this for years now, maybe getting on towards 8 years or so. Finally, this year, we had a version of the paper we were vaguely happy with. So we put it online in the archive where you can find it, and it's forthcoming in a book from Shanghai, actually a very nice collection of papers on the interface between consciousness and quantum mechanics. So yeah, look out for that book. But in the meantime, if you want to follow along, the paper has far more detail in it. You can find it online in the paper. I'll just hit a few key points along the way. Maybe somewhere in the middle, I'll throw in a few remarks about the shape of a mathematical approach to the science of consciousness. So you can kind of see the issue here, the issues in this talk is arising from the interface of two very deep philosophical scientific problems. Number one, what is the causal role of consciousness in the physical world? That's not quite the hard problem of consciousness, but it's very closely related to it. Yeah, how can consciousness play a role in the physical world? Number two, what is the reality behind quantum mechanics? How can the world be such that it supports the predictions that quantum mechanics gives us? And these are two very deep unsolved problems in science and philosophy. Just to start with the first, since I guess this is a consciousness crowd. So the consciousness causation problem is how can consciousness play a causal role in the physical world? And this is, I mean, this is a problem for anyone, materialist, dualist, and so on, especially for anyone who takes consciousness seriously. But a causal role for consciousness is especially elusive if you're inclined to accept that, consciousness may be something fundamental, perhaps non-physical, as I am, if you're inclined to accept that there's an epistemic and ontological gap between physical processes and consciousness, so it's not reducible to a physical process. If it's reducible, there are some more straightforward things you can say. And it's all the trickier if you also accept that physics forms a causally closed system. Roughly everything that happens in physics happens because of physics, happens with physical events have sufficient physical causes. And that seemed a very difficult, problematic to many people in the past. Sometimes I've explored denying causal roles for consciousness, as on the epiphenomenalist program. I've also explored looking at the idea that consciousness is fundamental but physical, are very deeply tied to the physical, the intrinsic nature of the physical, as on the panpsychist research program. But today I'm interested in kind of a more traditional approach to this problem, which is, possibly taking consciousness as fundamental, but arguing that it can actually play a causal role by denying the causal closure of the physical. And many people say that, okay, well, physics suggests that physical systems are causally closed, but there is this one giant loophole that's occurred to many people here. If you actually look at quantum mechanics, there's these very odd and somewhat anomalous events that are posited to happen regularly by a standard take on quantum mechanics, at least, namely the collapse of the wave function. So there's a tradition of taking this possible loophole and looking at it to give a causal role for consciousness. That's some large part of the motivation for what we're doing here. But let me now say something more about quantum mechanics. Quantum mechanics postulates this wave-like reality where things don't have definite properties. Nevertheless, we experience a world with definite properties. How can this somehow transition from quantum based to classical experience be explained? I mean, in classical physics, systems are described by definite values. Particles' positions are specified by giving a definite location and velocity and so on for the particle. But in quantum mechanics, systems are described by wave functions. A particle's position is specified not by a definite location, but by a wave function that has different amplitudes for different locations. So yeah, the top we have a classical particle with a definite position, the location of the dot. On the other spots, we have quantum particles whose position is specified by these wave functions with different amplitudes at different locations. And we say in these cases, the particle is in a superposition of location because it doesn't have a single definite location. It's representable as a sum of amplitudes of different locations. So a standard formulation of quantum mechanics, I mean, any formulation of quantum mechanics gives a very central role to these wave functions. And on pretty much every formulation of quantum mechanics, the wave function evolves according to the Schrödinger equation or something like it, a fairly standard linear differential equation by which this wave evolves over time. But at least according to one standard formulation of quantum mechanics built into the foundations by von Neumann in his textbook back in the 30s, and by many others since then, the wave function usually evolves. First, the wave function usually evolves according to the Schrödinger equation. But second, when an observable is measured, the wave function collapses probabilistically onto an eigenstate of that observable according to the Born rule. You get a definite result for the measurement, and the wave function now actually changes to be into a new state corresponding to that result, which is an eigenstate of the original observable. And this is a fairly standard textbook quantum mechanics. But this second part of the dynamics is at least been regarded by many as very mysterious. What is this collapse process? And when exactly does it occur? This says when an observable is measured, but what really does that mean? This is really the basis of the quantum mechanical measurement problem. What is measurement? It seems imprecise, vague, anthropomorphic, in a way that many people think is just inappropriate for a term used in a fundamental physical theory. Physical theories need to be precise. So, different people have responded to the measurement problem in different ways. One common response has been just the shut up and calculate response. This works really well for practical purposes. As long as it's working, let's not ask those further questions about what's going on in reality. Okay, fine for some practical purposes. Not so fine, I think, for many philosophers and indeed for many scientists' purposes. This has led to an avalanche of interpretations that don't give measurement a key role. Among the best known are Everett's many worlds style interpretation, David Bohm's hidden variable style interpretation, where there's no collapse and no role for measurement. Also spontaneous collapse interpretations, like the GRW interpretation that has collapse but doesn't require any notion of measurement to trigger it. These things just happen randomly under certain conditions. But there's a third approach that I really think has been somewhat neglected, and surprisingly so, in the foundations of physics. And that basically takes the idea that where you have something imprecise, an imprecise notion like measurement, well, let's make it precise. Let's precisify it, as philosophers sometimes say. And if there's multiple ways to precisify it, well, all the better. That gives us a whole space of possible theories that perhaps we can investigate and test. So that's the broad class of interpretations that we're exploring in this paper. You might think of these interpretations as measurement collapse interpretations. Keep the standard Schrödinger plus collapse dynamics, but replace measurement by some more precise criterion for collapse. In principle, there's a whole family of measurement collapse interpretations, depending on the precisification, which actually turn out to be empirically distinguishable in principle. Actually, towards the end of the talk, I'll talk about the program of experimentally testing these interpretations. But today, even if you're not interested in consciousness, I think the project of precisifying measurement is itself interesting and important, and there's some very cool interpretations to be looked at here. But current context, we're interested in consciousness. So I think especially salient is the class of consciousness collapse interpretations, where we give consciousness a role in understanding measurement. And there is a long tradition of doing this that goes back at least to, arguably you can find elements of this in people like von Neumann and London and Bauer in the 20s and 30s, although it's controversial exactly how to interpret them. Probably the locus classicus is Eugene Wigner in 1961, remarks on the mind-body question, and Henry Sapp and others have developed it more recently. This is the idea of understanding measurement as conscious observation. Understand measurement in terms of consciousness and say consciousness or conscious observation triggers collapse. And there's a few different motivations for this, depending on where you're coming from. One is it's a clear, natural trigger for a collapse. It does a particularly good job of saving the phenomena that we experience, a classical world, without superpositions and the like. And if you're interested, if you're motivated by the consciousness question, it's got the big bonus of providing a causal role for consciousness, potentially. So, potentially there's this holy grail of solving the consciousness causation problem and the measurement problem of quantum mechanics at once with a single theory. So this has been an attractive idea, at least to some people. Fair to say it has not at all been a popular idea, either among people working on the foundations of physics or among theorists of consciousness. And for a long time, I've been very skeptical about it myself, but I am inclined to think it's worth taking seriously and exploring. I mean, one major objection here is, well, how does it really help to replace measurement by consciousness? You've just traded in one mushy notion for another. Consciousness is just as imprecise as measurement. Well, maybe in some circles, people will buy that, but maybe I hope that that's got less of a plausible ring to it around here, where we have a whole bunch of people who are very much engaged in the project of precisifying consciousness. For a start, many have argued that once you sort through all the different notions of consciousness and fix on one, like phenomenal consciousness, a notion tied to what it's like to be in a state or to subjective experience, a number of philosophers and others have argued that phenomenal consciousness is not vague, at least in the sense that you either have it or you don't. And it's hard to make sense of borderline cases. So, I mean, that's somewhat controversial, but it's at least some reason for thinking that there's a precise notion here. Furthermore, maybe more to the point in the present context, there are now precise mathematical models of consciousness aimed to give something fairly close to precise conditions for where consciousness exists and maybe for exactly what kind of consciousness there is. And probably the best known of these theories is integrated information theory, which I'll go on to discuss shortly. But in principle, the approach here could be combined with any precise mathematical model of consciousness. It's worth noting that, consciousness collapse approaches of this kind, they're actually neutral on the question of materialism versus dualism about consciousness. I'm myself sympathetic to a kind of property dualism, and causal roles for consciousness and model. But there's nothing about this whole approach that requires property dualism. If you're a reductionist who thinks consciousness is identical, say, to some physical property or some physical correlate, then you might still be interested in the causal role for consciousness, and you might still be interested in consciousness or the physical correlate playing this distinctive role in collapse. So this is in principle interesting to both, but especially interesting for the dualist, for whom it might potentially solve a big problem about the causal role of consciousness. Anyway, our central project then is to spell out the precise dynamics for consciousness collapse models. We think the biggest problem for this is not that it's imprecise or anthropomorphic, not that it's dualistic, simply that it has never really been spelled out terribly precisely. To evaluate that, we need a precise version of this with the precise dynamics, then we can make sense of it. So basically what we try to do in this paper is to use a mathematical model of consciousness, namely IIT or its quantum mechanical version, and a mathematical dynamics of collapse, namely a version of the continuous spontaneous localization collapse theories developed by Philip Pearl and others, to minimize unclarities and to make this dynamics as precise as possible, with the aim of making the approach precise enough to be assessed. I think it's important to say here we are very much exploring the idea. We're not asserting that it's correct. I think it's fair to say that neither, if you ask Kelvin or me, do we actually believe that the claims that this model is true, is correct? I think we both be somewhat skeptical about that. But I think we both think it's an idea at least worth exploring, so that we can evaluate it. As a matter of fact, the results are mixed. When we first started on this project, we had the idea it could be done in some very clean and simple way. Well, it turns out to be complex. Turns out you've got to make some compromises, but at least it seems that there's a research program worth exploring here. So the guiding idea really about, I mean, there's actually been a number of approaches to combining consciousness and collapse in recent years. One of the best known is by Kobe Kremnitzer in a paper from a few years ago, where he brings in an interaction of collapse and IIT, and there have been some other really interesting approaches too. I've had more time and explore the relations. But the distinctive feature of our approach is that consciousness serves as what we call a super resistant property, a property that resists entering superpositions. And this is what somehow drives the whole collapse process. And this is, I think you can arguably find this idea in a sentence in Wigner, where he seems to suggest consciousness couldn't enter superpositions because somehow the system would enter suspended animation. You can find the idea in David Albert, just in trying to make sense of this model. Not that he's an advocate of it at all. I explored it very briefly in something I wrote 20 years ago. But the basic idea is that consciousness or its physical correlate, which I'll call here the PCC, the physical correlate of consciousness. You all know the neural correlate of consciousness. Here I'm just trying to be somewhat more general, so I'll call it the PCC. And the guiding idea is that consciousness or its physical correlate is superposition resistant. The extreme version of this is what we might call absolute superresistance. Consciousness or its physical correlate cannot enter superposition. It is barred from entering superposition. This is what this involves what physicists call a superselection rule for certain operators associated with consciousness or its physical correlates, whereby the system is basically required to be in an eigenstate of those operators throughout, can never enter superpositions, and then you actually get a pretty straightforward dynamics. I mean, it's initially attractive, this kind of superselection idea. Yeah, consciousness can't enter, the rough idea is consciousness can't enter superpositions, its physical correlates can't enter superpositions, they're always in definite states, they will always collapse anything they interact with, that they get entangled with. So we take an electron in a superposition, say, of positions, S1 plus S2. Then we perceive the electron. And according to standard quantum mechanics, basically then you get we had a superposition of electron states, now we have a superposition of electron plus brain states. Let's just focus on the consciousness part of the brain state, call that C. So now we have a superposition of the electron being on the left, and you're experiencing the electron on the left, plus the electron being on the right, and you're experiencing the electron being on the right. But that would be a superposition involving consciousness. And say, okay, well, that cannot happen according to this superselection idea. So it follows at the moment where consciousness would enter a superposition, in fact, it's got to collapse probabilistically to one of these states. Let's say the second one, appearing that the electron is on the left, which will have the result that the electron, which is entangled with it, will also collapse to a definite position. Result, you'll have a definite state, the electron's in S1, and you'll be conscious of the electron being in S1. So, okay, that's nice. Consciousness is collapsing all the stuff around it, kind of as we wanted for a consciousness collapse view. So this is particularly simple. Unfortunately, it has a fatal flaw. The absolute super resistance version, we call the Zeno problem because it can be linked to the quantum Zeno effect. But the basic idea is that superselection observables that can never enter superpositions can't actually change their values. Basically, if you're kind of to evolve from one eigenstate to another eigenstate, you have, an observable, a system has to go through a superposition of eigenstates. It's just a mathematical fact. If you constrain them to be in eigenstates throughout, they can't change their value, which has the rather unfortunate consequence that, say your system starts in a state of non-consciousness, and you might have wanted it to evolve into a state of consciousness. Maybe you're in the early universe and there's no consciousness. And at some point you might have thought consciousness would evolve? Well, basically, it turns out by the mathematics of superselection that no, there's no way for a consciousness ever to evolve. Basically, the idea is as soon as there's some branch with some glimmer of consciousness, it's going to collapse back onto non-consciousness with probability 1. Okay, so that's not too good. Consciousness can't get started in the early universe. Worse, you can't wake up from a nap. If you lose consciousness, you'll never regain it. Worse, your state of consciousness will never change. Okay, so the strong version, absolute super resistance, is not going to work. That said, there's a natural second best approach here, which is what we call approximate super resistance, which is rather than saying that consciousness absolutely resists superposition, we say consciousness or its physical correlate tends to resist superposition and collapses towards eigenstates. States of consciousness get localized very quickly, but without absolutely resisting superposition. Now, there are some downsides here. It's certainly a bit less clean than the absolute super resistance models. Furthermore, it requires us to tolerate some superpositions of states of consciousness. It's actually far from obvious what it would be to be a superposition of state of consciousness. You know, Wigner thought this was impossible. Now we're having to tolerate them. I view that as a major cost for the view, but in the paper, we talk about ways to understand superpositions of states of consciousness. But there are also some upsides here too. There actually is fairly well understood dynamics for approximate super resistance, coming from the kind of continuous spontaneous localization collapse theories that have been developed by Philip Pohl, Angelo Bassi, Laios Diosi, and others. Roughly continuous collapse dynamics for arbitrary operators, which generalize the, Pohl did it for mass density operators. It turns out it's not that hard to generalize it. So there's actually a bunch of math available off the shelf that can help develop an approximate super resistance model. So that's really our project here. The overall dynamics is instead of having absolute super resistance, let's have this approximate super resistance, which is continuous CSL style collapse onto a consciousness basis or onto a physical correlate of consciousness basis, if you prefer, where the consciousness basis, well, at least at the physical level, that's going to be a set of commuting operators that define a physical correlate of consciousness given by a physical theory, given by a mathematical theory of the physical basis of consciousness. And we'll use integrated information theory as our mathematical theory of consciousness in what follows. And you could use other theories, but it's the best developed theory with this form. And we'll use the version of it that's been adapted to quantum systems as developed by Johannes Kleiner and Stephen Tull, who are here, and Philip Zanardi and others who are out there. Sorry, Sean Tull and Philip Zanardi and others who have written interesting papers on quantum IIT. So a bit more on that shortly. But basically, you can view what we're up to here. If the details are become a little bit heavy for those without a background in relevant areas, you can think of this as a kind of mashup of ideas of Wigner on the one hand, Philip Pohl on the other hand, and Giulio Tononi on the third hand, where we're basically taking over. What we basically need is a psychophysical theory of consciousness, of connection between, say, physical basis of consciousness and conscious states. And there we're using Tononi's theory with a theory of how consciousness stochastically resists superposition. The generic idea comes from Wigner. The mathematical details come from Pohl. I mean, the basic principles are that, Tononi has a principle that consciousness goes along with something that people sometimes call Q-shape, a certain kind of qualia shape, which can be physically definable. We can take that as a psychophysical principle. Consciousness covaries with Q-shape, then combine it with this principle that consciousness stochastically resists superposition to get Q-shape stochastically resists superposition, and a nice dynamics develop from there. Okay, so that's the basic shape. Now I'm just going to present a few more details and maybe a bit of reflection on the shape of a mathematical theory of consciousness. I'll start with, before getting to the quantum mechanics and the CSL, I'll start with a certain way of understanding integrated information theory. I mean, IIT, it's a beautiful theory. Personally, I have kind of a love-hate relationship with IIT. I like many features of it. I find it attractive and appealing, but it's also got many problems that lead to a lot of worries. Advantages, and I mean, number one in this context is mathematically precise. That's really handy in this context. Number two, particularly appealing to me, it uses informational structure. Back in my 96 book, I argued that the physical correlates of consciousness were probably best understood in informational terms, differences that make a difference. That's precisely the kind of structure that IIT exploits. It also, once you look at the details of qualia shapes and the like, it has a particularly suggestive form, I think, for a general psychophysical theory. So that's attractive. On the other hand, problems, I mean, famously, the empirical support is rather weak because it's very difficult. I mean, it's very difficult to actually measure these IIT quantities in the first place, and to test them in physical systems. So an awful lot of the support is kind of either very broadly phenomenological, coming from Tononi's phenomenological axioms, or just coming from very generic features like integration matters to consciousness rather than the precise mathematical details. So I think the empirical support, it's fair to say, is fairly weak to date, at least to distinguish it from other complexity-based theories. Another worry is that the connection to physics is actually surprisingly ill-defined. You define IIT properties in terms of network properties, not in terms of physics. So there's at least a gap there to be closed. And finally, the phenomenological predictions are somewhat unclear. IIT associates physical systems with this degree phi, or with these structures, Q shapes, but it's kind of not at all clear what those come to phenomenologically. I mean, my ideal here is a mathematical theory that maps physics to phenomenology. It turns out that IIT gets kind of close to doing that, but it's not actually right there on connecting to physics. It's not actually right there on connecting to phenomenology. But I kind of imagine a more developed version of this. Maybe this is IIT 4.0 or IIT 10.0 or something that ends up making the connection to physics and phenomenology more directly, and then we could really use it here. Okay, so IIT maps network structures and maybe eventually physical systems to a couple of different things. Most famously, it associates it with a degree of consciousness, phi, which is a scalar real quantity. I actually am much less interested in phi than I am by this other thing, which potentially represents the structure of consciousness, sometimes called a maximally irreducible conceptual structure in IIT, or a mix. Occasionally, a couple of times, IIT theorists have used this word Q shape for qualia shape, which I like a whole lot better. So Kelvin and I use Q shape in our discussions of this. And this is actually interesting because it's not just a measure of degree of consciousness, it's a potential measure of the whole structure of consciousness. It's an extremely high dimensional quantity that, at least in principle, could represent very much of the structure of consciousness. Both of these, I'm not going to go into the mathematical details of how these quantities get associated with systems. Very roughly depends on integrated information, which is very roughly the idea that certain systems or certain subsystems have effects, play a causal role that aren't just simple sums of the effects of their parts. They kind of have irreducible causal powers in a certain sense that one can define. And that ends up being what's crucial to defining phi and to defining these Q shapes in turn. Q shapes, which I'm interested in, are basically they're complex mathematical structures. If you've got an n-element network in IIT, you'll assert its Q shape will involve 2 to the n minus 1 points, each of which inhabits a very high dimensional space with 2 to the 2n plus 1 dimensions. So again, I'm not going to go into the details here, but it turns out that for an n-element system, you can specify the Q shape using 2 to the n minus 1 times 2 to the 2n plus 1 parameters. So it's a very high dimensional quantity. And the idea is that, I take it the idea is that Q shape somehow represents the structure of the conscious experience associated with the system. I've never gotten very clear on exactly how this is meant to work. What is the phenomenological decoding of a Q shape is as phenomenology? What corresponds phenomenologically to what? I've asked the IIT proponents for a Rosetta Stone by which you can actually decode these Q shapes into phenomenology. And again, I'm hoping that that comes with a future version of the theory, because I think that's the kind of thing that ought to be possible in principle with the structure of consciousness, ought to be mathematically representable. It ought to be, you could write down things, you could write down mathematical states that via some kind of decoding correspond to phenomenal states, or at least to phenomenal structures. So here's how I think of the role of Q shapes in a theory like IIT. It's a form which I think applies to potentially to many different mathematical theories of consciousness or of the structure of consciousness. We basically have these abstract objects, Q shapes. They're just straight mathematical objects. Intuitively, they correspond to the structure of consciousness, but they're just mathematical objects. And then we have two different notions of physically realizing a Q shape or phenomenally realizing a Q shape. A system physically realizes a Q shape. Well, that's going to be, when certain network conditions or physical conditions are met. And that's where you get all the equations of IIT and the complex sums over partitions and measurements of phi and so on. All that can basically be taken to define a mapping from network states to Q shapes, or equivalently, a set of conditions under which a given Q shape is physically realized. So you think of that as like a physical definition of physically realized Q shapes. At the same time, we have a notion that a Q shape is phenomenally realized, and that's purely phenomenological. We take this mathematical object and then we break it down into phenomenal elements, and here is where we need that Rosetta Stone that doesn't yet seem to fully exist for IIT's notion of Q shape. But we know what's going to correspond to a phenomenal dimension, what's going to correspond to a location in a phenomenal quality space, what's going to correspond to something like analogous to the whole part structure of a visual field, and so on. But in principle, I don't think that has been done yet. But I think in principle, I could imagine for any given account of the mathematical structure of consciousness, it's great to have the math, but we also want to be as clear as possible on what that corresponds to phenomenologically. And it's far from obvious exactly what the right vocabulary for doing that is, but this kind of thing already exists for certain things like, say, phenomenal quality spaces for color and so on. We've got like mathematical characterizations of color experiences, and we know how to decode that into phenomenal dimensions on this axis and that axis. Okay, so we've got Q shapes, we've got physical and phenomenal realizations of them. And then the way I understand a theory like IIT is it basically says, here is your fundamental psychophysical principle, or psychophysical law, if you like. A given Q shape is physically realized according to the IIT definitions, if and only if it is phenomenally realized. So these mathematical objects, Q shapes, kind of serve as the bridge between say physics and consciousness. And the physically realized Q shapes and the phenomenally realized Q shapes always have to be identical. And I think this is just in general a nice structure for a mathematical theory of consciousness, independent of IIT, at least if you're inclined to the kind of theory on which conscious states depend, supervene on physical states, and in some kind of mathematically precise way. I think you can argue, and if you think that that states of consciousness have mathematically specifiable structures, then it ought to be possible to put your theory of consciousness in something like this form. So this is a very nice structure for a theory to have. I mean, it's far from clear that this would be a complete theory of consciousness. There are some obvious objections to the completeness of a mathematical theory of consciousness of this form. There are some very familiar reasons to think that mathematical structure might underdetermine states of consciousness. There are those qualia inversion cases, two states of the same structure, but one person experiences red where the other one experiences green. There's things like the Mary case. Mary knows the complete mathematical structure of a state of consciousness, but she's still not in a position to know what it's like to see red. So, I mean, you can use these familiar considerations to argue that mathematical structure doesn't exhaust states of consciousness. But even if that's right, mathematical structure still could be very much at the core of a state of consciousness and can provide a whole lot to be going on with and doing science with. And that's how I see its role here. Okay, so basically then how do you combine this way of thinking about IIT with the super resistance idea in quantum mechanics? Well, the rough idea is, okay, consciousness was super resistant, right? Consciousness resists entering superpositions. Well, more precisely, we'll now say, sorry, that should say phenomenal Q shape is super resistant. Systems, will resist going into phenomenal states, which are superpositions of different Q shapes. And because phenomenal Q shape is nomenologically tied to physical Q shape, the fact that the shape of consciousness resists superposition will entail that the physical Q shape, realized in, say, in the brain, will also be super resistant. So, to turn that into math, basically, okay, well, we have to specify Q shape using a whole bunch of parameters, 2 to the n minus 1 times 2 to the 2n plus 1 plus 1 parameters, and then associate every parameter with a quantum operator. You can view each of these parameters as a quantum observable, associate with an operator. If we were working with absolute super resistance, we would make every one of these a superselection operator that cannot enter superpositions. Since we're working with approximate super resistance, we'll instead say that each of these obeys localization dynamics. And there's fairly familiar ways to do that for arbitrary operators. Okay, at this point, I copied a slide from Kelvin, since it was just a nightmare to put the math into Keynote. This is all Kelvin's version as PowerPoint. Yeah, at this point, we brought in some quantum integrated information theory, which has the nice property of already being very well adapted to the quantum context. It's not totally obvious that classical IIT definitions are well defined in a quantum context, whereas Zanardi, Kleiner et al. Have developed quantum versions that are well defined in this context. So, and actually, Johannes gets a lot of credit here. We work with him, and he came up with a nice formulation of these collapse operators for IIT in the quantum context. And Johannes is a co-author on the relevant section of this paper. So in quantum integrated information, classical probability distributions get replaced with density operators. The distance measure changes a little bit, but there's a bunch of fairly straightforward math for representing collapse operators by a whole bunch of coefficients, and then defining Q shapes in terms of certain sets of coefficients, C, I, J, K, and a bunch of real numbers for the phi values. This is all kind of IIT arcana. Anyway, I don't have time to go into the details, but you get a nice definition for a whole bunch of Q-shaped operators, Q, I, J, K, for different values of I, J, K. These are the different dimensions of Q shape, where it's just a sum of this complicated quantities involving the phi values and the Cij values applied to quantum states. So it's got these basically gives you an operator on quantum states for each of the dimensions of Q shape. There's a bunch of complicated stuff here about translating from classical, what we call classical Q shapes, to quasi-classical Q shapes under quantum IIT. But here you'll just have to take the details on faith, since it's clear I don't have time to go into them properly. Okay, so that's the operators. Then standard CSL, continuous spontaneous localization, Pearl's version, applies to mass densities and basically says mass densities resist superposition. Many of you will know GRW that does all this kind of discretely. CSL is basically a continuous version of this, where superpositions of mass density gradually collapse towards definite mass densities, eigenstates of mass density. But it turns out the dynamics can easily be generalized to arbitrary collapse operators, and a number of people have done this in the foundations of physics literature in recent years. Angelo Bassi has, I think, been one of the ones who put forward the most general form. I mean, for mass density collapse models, you basically have a version of this. It's basically the standard Schrodinger equation, which is the first term, plus some stochastic terms for stochastic collapse, depending on these stochastic W terms, Wiener processes. Yeah, here we have, in the second half of the slide, you've got the form for mass density. In the first part of the slide, you've got the form for generalized to arbitrary operators, as developed by Bassi, where A hat here is the relevant collapse operators. Lambda is a parameter for collapse rate, and you've got these in these Wiener processes. So okay, all we really have to do is take that now and apply it to our Q-shape operators, and we get a nice equation, which you can write like this. Again, it's just the first part, it's just the basic Schrodinger equation, and then we've got these stochastic terms involving these, which give a role to these Q collapse operators, depending on lambda and with these associated stochastic functions. You have to sum them. I mean, there's a whole lot of the Q operators. They vary. Remember, it's very high. Q shapes are very high dimensional, so we have to sum these things over IJK. It turns out if you've got a state that's got just a superposition of very closely related Q shapes, then the Schrodinger term will dominate, and you'll just get very slow collapse. But if you've got a system which is in a superposition of very different Q shapes, then there's going to be collapse is going to be much more significant, and the system will collapse towards a joint eigenstate of the collapse operators at a rate proportional to their eigenvalue differences. Okay, so that's basically the way of taking this whole framework and combining IIT and CSL into a mathematical collapse model. And again, the basic idea is consciousness resists superposition, so phenomenal Q shapes do, so physical Q shapes do, and everything that these things interact with will thereby also undergo continuous collapse via fairly standard quantum dynamics. Okay, looks like I'm running out of time. Let me just say something about experimental tests and then something about objections, and I'll be done. One nice thing about this whole program of collapse interpretations of quantum mechanics is different super resistance models with different collapse operators actually all make different predictions. So we've actually got a whole bunch of experimentally testable different theories here. They're testable in principle. I mean, the standard way for testing these kinds of things is basically by detecting superposition by finding out if certain interference effects are produced. Usually interference effects, as in the double slit experiment, are consequences of superposition. If you don't find interference, then it looks like there's no superposition there. It just turns out that in complex systems, this is very hard to test because you've got to prepare these systems in great isolation from their environment. Otherwise, you get decoherence, which is kind of indistinguishable from collapse. So these are very difficult experiments to do, except in simple systems. But there is a project of doing these interferometry experiments in more and more complex systems. It turns out, anyway, that for the very simplest IIT collapse model, the one we've actually defined so far, where any superposition of Q shape collapses the wave function, that kind of IIT collapse model may already have been tested and indeed falsified, which is what anyone familiar with this area would actually expect. Here, Kelvin and I started thinking about what's the simplest system which can enter superpositions. Well, it's going to be the simplest system that can have two different Q shapes associated with it, which in IIT is a kind of dyad, two elements which may or may not have certain connections between them. It turns out you can get a non-zero Q shape, a non-trivial Q shape, when there's a swap dynamics between them. The value of A goes into the value of B and vice versa. Anything else gets a trivial Q shape, a null Q shape. So, okay, just say you've got a two-element system in a superposition of a swap state and a non-swap state. That's going to be a superposition of Q shapes. And then if the literal IIT collapse interpretation is correct, that ought to collapse. You should not get persisting superpositions of this system, at least if the collapse is fast enough. So you shouldn't get certain interference effects. Okay, well, I mean, it seems that ought to be pretty easily testable. In fact, one very immediate intuition is surely this has been tested already with experiments in quantum computing. my own view is that, you know, if you look at quantum computing with Fredkin gates, you find something that looks at least a whole lot like a superposition of swap states and non-swap states, where we've actually gotten the kind of empirical results people would expect from quantum computing, which involve this kind of interference. If that's right, and if that really is a superposition of Q shapes, then it looks like we've at least falsified the simplest version of this, where, yeah, any superposition of Q shapes collapses the wave function fast. Kelvin is somewhat skeptical that Fredkin gates are really a good example of this, because it turns out they have a feed-forward structure. What we really need is something with a relevant feedback structure, and that requires coherent quantum feedback. Anyway, finding exactly the right quantum computing experiment to falsify this is an interesting project, but you know, anyone remotely sensible is going to assume that this can be done and tested, and I think, you know, very few people would actually expect that we're going to find the remarkable result that dyads, two-element dyads, can collapse wave functions. That's not something anybody expects. So really, okay, that's nice. We've actually falsified the simplest version of a theory, and now we have a program of experimentally constraining more complex versions. So here's a program of experimentally constraining information/collapse theories via quantum computing and other methods too. Eventually, you can imagine that, you know, with time, as quantum computing develops more and more, and we move from, you know, 10 qubit systems to 100 qubit systems to thousands of qubits. Eventually, we might test whether a quantum simulation of the whole human brain leads to collapse. I mean, it's hard to do an interference experiment on a human brain. Probably the brain wouldn't survive it, but you can do it. So you can do it in principle on quantum simulations of human brains, and that would be super interesting, and see whether quantum simulations of human brains lead to collapse. Now, if you did get collapse, well, that would be remarkable and interesting, and would tell us, okay, yeah, no interference from human brains, there's collapse here. Then we'd have a very strong clue, at the very least, about collapse taking place, about the locus of collapse. Collapse experiments could strongly constrain the locus of collapse, at the very least, which will be of interest to anyone in the foundations of quantum mechanics. And if you're inclined to believe that there's a tie between consciousness and collapse, this would then strongly constrain the locus of consciousness, which gives rise to this, you know, this program of actually getting empirical clues about the physical correlates of consciousness from these interferometry and other collapse experiments. Okay, now you probably have a million objections. I've just mentioned a couple. So if I mentioned already what is a superposition of consciousness, how does that even make sense? Very good question. I'm not sure it makes sense, so it's a reasonable objection, but we do spend some time talking about this in the paper. There's also the question of whether this really gives consciousness a causal role, and if it does, whether it gives it the kind of causal role that we antecedently wanted, which is also a complex question we discuss a lot in the paper. I mean, one thing you might say is, how do you know phenomenal Q shape is collapsing the wave function? Maybe it's just physical Q shape. I mean, if you're a materialist, those two things will be the same. So we'll get a causal role for consciousness either way. If you're a dualist, you might want to say, yeah, couldn't there be quantum zombies that just have physical Q shapes and they collapse the wave function? And maybe that's what's doing the work in this world. To which I think we want to say, well, yeah, that's one way a world could work. But our hypothesis that gets all this going in the first place is actually consciousness that's super resistance. It's the super resistance of phenomenal Q shapes that makes physical Q shapes collapse, and that collapses everything else. So that really gets consciousness playing a key role in the dynamics. It does turn out that there are going to be other versions of the dynamics, which may be empirically equivalent, that don't give consciousness a role. We're prepared to take that on board. But if you don't like that, there are more radical versions of this that allow, you know, consciousness to play a special causal role that violates the quantum probabilities and gives you something special and empirically testable. We're not prepared to go that way ourselves, but I think it's at least an idea worth exploring. Okay, so I think my time is up. So advantages, so results, as I said, are mixed. Advantages, we have a reasonably clear and precise dynamics for consciousness and its role, potential role in the physical world, experimentally testable in principle. Disadvantages, it's certainly not as simple and powerful as the original collapse idea. the version spelled out by von Neumann, or even the absolute super resistance idea. It's complicated. It also countenances these consciousness superpositions, which is certainly something to worry about. Still, I think, there's at least we've got an existence proof of a certain kind of consciousness collapse model here, as of others put forward. Here, I think, maybe there's now a challenge for others to improve on this and see if they can do better. So at the very least, I think here, there's a research program worth exploring. Thanks.